So we complete the remaining parts of our lecture. So we have here the torsion function. The torsion function. What is the torsion function? We can say that the torsion function of a number is all the numbers that are not divisible by that number. For example, so it is all numbers less than this number and not divisible, not dividing this number, not dividing this number. So all numbers less than that number and not dividing this number. For example, I can say the quotient, and this is the sign of the quotient function of 5. The quotient of 5 equal, the quotients of 5 equal 4. Why? Because I have 4, 3, 2, and 1. 4, 3, 2, 1, they are all not dividing the 5. Okay, so I have the quotient of 5, 4, 3, 2, 1, including 1. So the quotient of 5 equal 4. How many numbers are not dividing 5? Okay, so we can say relatively prime to 5. All these numbers are relatively prime to 5. All these numbers are relatively prime to 5. Other example in the textbook, you can see it. 537 equal, 37 is a prime number. So this is going to give us Q, which is a prime number, minus 1 equal 37 minus 1 equal 36. So the quotient of 37 equal 36, just because I know that the prime number is not divisible by any number beneath it. All numbers beneath it are all co-prime to it, or relatively prime to it. So phi of 37 equal 36. What about phi of 35? Phi of 35, I can say I have to list all of these numbers. Maybe, 5 is not going to be included, 7 is not going to be included, and so on. Because, 5 divides 35 and 7 divides 35. So this way, I can say, I can list how many quotients out there. I can say 1, 2, 3, 4, but no 5, because 5 divides 35. I can have 6, 8, 9, 10 is not going to work too, because they are not co-prime. They have common number, which is 5. They have common number, which is 5. So 10 is not going to be included. 11 is okay. 12 is okay. 13 is okay. 16 is okay. 14 is not going to be there, because they have 7 here, and 14 and the 35, they have common divisor, which is 7. 16, 17, 18, 19, 22, 20 is not going to be included, 23, 24, 26, 27, 29, 31, 32, 33, 34. All these numbers, if you count them, you will find that phi of 35 equal 24. If you count these numbers, you will find them 24 numbers. All these numbers are relatively prime to 35. All these numbers are relatively prime to 35. Okay, these are the quotients, and if you open page or slide number 32, slide number 32, you will find quotients for many numbers. For example, for 4, we have 2 values. Quotient is 2. 5 is 4. This is the number which is n, and this is 5n. I just to give you some example. 5, what about 7? 6, because 7 is a prime number, and the corresponding quotient value is 6. 10, we have 4. Also, we have 29, 28, because 29 is a prime number. And 30, we have only 8 co-prime numbers beneath it. This is the quotient function. Quotient function. It's clear that phi of p equal p minus 1 if p is prime. Of course, I can guess it. I can see that. And also, there is a great property here. If phi of n and n can be constructed or decomposed as 2 prime numbers multiplied by each other, so like PQ, so PQ equal N. This means I can have the quotient of P multiplied by the quotient of Q. This is going to give me, because if P or Q are primes, this means phi of P, so it is going to be P minus 1 multiplied by Q minus 1. Okay, let's have an example for this. If phi of 21, I can't calculate the phi of 21. It is difficult. So it is better to have it. This is as a multiplication of prime numbers. So I can say phi 3 by 7, and 3 is a prime and 7 is a prime. This is going to give me phi of 3 multiplied by phi of 7. This means phi of 3 is 3 minus 1 multiplied by 7, which is 7 minus 1. This is going to give me 2 by 6, which is 12. Okay? And that's it for the quotient function. Now I can apply the quotient function for Fermat's theorem. I can extend Fermat's theorem to Euler theorem. This is an extension of Fermat's theorem. It states that a to the power phi of n is congruent to 1 mod n. And also the other version, which is a to the power phi of n minus 1, or plus 1, sorry, plus 1, is congruent to a mod n. This is another shape of Fermat's theorem, as we have seen in the first part of this lecture. Now we move to very important property, very important algorithm, which is Miller-Rabin algorithm. Miller-Rabin algorithm. Miller-Rabin algorithm is just to test for primality. Test for primality. Test for primality. I can say primality. It takes a very big number, for example, 3, 2, 5, 2, 1, 5, and check if it is prime or not. The algorithm is written on the slides. I don't want you to keep it, or I just want you to know that there are an algorithm named Miller-Rabin that may be used for testing the primality. I can check if this number is prime or not, just that. But it doesn't give us an accurate answer. It just gives us probability because the big number is very hard to test for primality. And many other algorithms tried to test for primality, but this is Miller-Rabin has different versions that we can have an accurate answer for even testing if this is a prime number or not. Anyway, I don't want you to recite the algorithm. I just want you to know about it. There is an algorithm existing there. We can use it to test if a number is a prime or not. Okay. There is a theory called Chinese remainder theory. Chinese remainder theory. The theory states that it is possible to reconstruct integers from certain range for a certain range from their residues modulo a set of pairwise relatively prime modulo. Okay, what the meaning of these now? If these words, for example, I can construct x as collection of numbers mod m1 and x is equals congruence with a2 mod m2 and x is congruent to a3 mod m3 and so on. What does this mean? It means that I can represent a number with a collection of modulo numbers, and these numbers are the they call it what, relatively prime factors of x. The relatively these m1, m2, m3 are relatively prime factor, relatively prime factors of x. Okay, the relatively prime factors of x. Okay, okay, let's have an example. This is actually not the okay. Let's take an example is better than the definition. M1, M2, and M3 should be relatively prime. We can say, okay, it's better to say they are primes. This is a collection of primes. I will tell you an example right now to give you the overview of this algorithm. This is an overview of this algorithm. So for example, I have here, if I am taking mod 10, mod 10. Okay, I can construct the mod 10 by using two mods here, mod 2 and mod 5, where 2 and 5 are the relatively primes of 10. The relatively primes of 10. So when you multiply 2 by 5 is 10. This means I have the relatively prime numbers of 10. For example, if I have x mod 2 equal 0 and x mod 5 equal 3. This way I can define this number, I know it is between 0 and 9, just because it is mod 10. How do I know it is mod 10? Because I can multiply 2 by 5, so it is 10. So the number must be between 0 and 9. And also, this number is even number. This number is even number because the division by 2 gives no remainder. So it is even. And also, when this number is divided by 5, it gives a remainder of 3. This means that this is an even number, and it gives a remainder of 3 if it is divided by 5, and it is between 0 and 9. This means the only one is 8. So x equal 8. This is no way. All these conditions, even numbers, 8 mod 5 equal 3, and it is between 0 and 9. How did I know that it is between 0 and 9? Because I can construct x using its the base here, which is 9, is 10. If I multiply 2 by 5, it's going to give me 10. So this is the Chinese remainder theorem. Chinese remainder theorem. The last thing I want to present here is the discrete logarithms. And this is very important. We will face it many times, discrete logarithms. For discrete logarithm, okay, I just want you to concentrate on something. If I want to have a number here to the base 3, and this number mod, for example, 7, will give me range of numbers from 1 to 6. This is going to give me numbers from 1 to 6. I want to have this mapping. For example, I can enter any number for x, and always give me this range between 1 and 6. 1 and 6 because I have here 7, so it gives me all numbers between 1 and 6. Why is that? Because we are going to use this exponent in our algorithms after that. Because if you want to solve a problem like that, you can use logarithms. For example, 10 equal 3 to the power x. You can take len of the two sides. So len 10 equal x len 3. This way I can have x to be as len 10 over len 3. So I can have x here. I'm using logarithms, okay? But here this is for normal mathematics, not for discrete logarithms. Let us test this if it is working or not. For example, I can say 3 by 1 mod 7 equal 3. 3 by 2 mod 7 equal 2, because this is gonna have 9, and the difference between 9 and 7 is 2. This is 3 by 3 mod 7 equal 6. You can count this. 3 by 4 mod 7 equal 4, and 3 by 5 mod 7 equal 5. 3 by 6 mod 7 equal 3 by 5. 3 by 6 mod 7 equal 1, and 3 by 7 mod 7 is going to give me 3, and 3 by 8 mod 7 is going to give me 2, and so on. So if you see, we have here the same cycle repeats, start to repeat here. The same cycle start to repeat again here. 3, 2, 6451 and then 326541. This way I have this cycle. I succeed to create this cycle using that exponent, and I can now have the ability to calculate this x. For example, for example, if I have something like 4 equal 3 to the power 6, 3 to the power x mod 7. This is an example. 3 to the power x mod 7. I know this is going to give me 3 to the power x mod 7. If it equal 4, this means x is 4. So x is 4. Here x is 4. Okay? And then another example. 6 equal 5 to the power x mod 7. I know that if the result is 6, this means x is 3. So this means x is 3 from where? From this one. So this is going to give me x equal 3. Okay? You can test this. It's going to give you a correct answer. And that's all for this lecture. Thank you for listening to me. Thank you for today's attending and concentration on the content of the lecture today. All mathematics, but they are very important to understand the subject of cryptography. Good luck and see you inshallah next week.